Hi, we are continuing the discussion with the non-ideal transistor behavior, and we will talk about the leakage now. And the leakage, if I may go to the whiteboard here a little bit, and we'll draw the transistor in much, remind ourselves with the major components of the transistor. So here we have the source, the drain. We've got this SiO2 layer, okay, SiO2, and then we have the gate here. Okay, so this is the gate, and basically we have what we call the leakage current, the leakage currents in this device. Um, so the leakage current in this device, first of all, what is leakage? Leakage are all those types of currents that are undesirable that happens in the device, and we don't want them, but they do happen because of the imperfection that is in the design and in the device. Because no matter how good we make these things, there are these currents that leaks, and honestly, they tend to waste battery and energy, and they tend to be hard to control. Okay, the very first leakage current is the subthreshold current. The subthreshold current. And a subthreshold leakage current, what happens is that when this device is in and off, you see when we draw the current versus IDS, I'm sorry, versus VGS. Okay, so this is the current and VGS, and we used to draw like this, and this is VT. Okay, and basically less than VT is zero. All right, so this is what we used to say. This is zero. Well, we lied. It's not really zero. If we zoom in this area, we will see that the current basically rolls down to smaller values around VT, sort of like exponentially, but it is not never like an immediate drop. It does not go like so this is the way it does, okay, but it never goes like this. So this is the current goes to VT and doop, it goes to zero. No, that's not the case. It rolls down all the way to smaller and smaller values. So if VGS less than VT, we still have some amount of current, okay, and that is the leakage current. This is typically in the device when it is in what we consider the off device, and then we have again the subthreshold current. To reiterate, it is the current that happens in the device, current that is being leaked between the source and drain when the VGS between VT and 0 volt. Then we have the gate leakage, and the gate leakage basically when the device is on, and basically when the device is on, and because of high electrical field in recent processes, this thickness of the oxide, which is TOX, is becoming smaller and smaller and smaller, and electrons they gain energy, and it becomes easier for them to penetrate this isolating area and go to the gate. So there is this tiny leakage that occurs when the device is on, and that is called gate leakage. And finally, the junction leakage, or the diffusion leakage. Okay, the diffusion leakage. All right, diffusion leakage, and basically these are because of these reverse bias diodes. All right, that is between the source and drain and the P substrate. Yes, they are reverse biased PN junction diode, but there is a current in these reverse bias diodes. Okay, but typically this is ignored really because of small amount of current. Okay. Uh, so this is the junction. Let me say this is the junction. Okay, leakage. All right. So now, so let's go back to the slides, and now we can see with this introduction, okay, that we have these three types of leakages. The subthreshold, as we indicated, between the VGS between 0 and VT. This is because the current does not drop immediately after VT to 0. Rather, it rolls off exponentially down to smaller and smaller values. Um, and between VT, when VGS between VT and 0, this is when this typically occurs, and this is when the device is in off state. Gate leakage, on the other hand, it is typically we assume that there is no current goes through the gate, but basically as the thickness of the oxide it gets smaller and smaller, then some electrons tunnel through this thin layer of TOX and going to the gate and making gate leakage. Okay, and then the diffusion leakage, which is basically the reverse bias diodes that we talked about. Okay, one thing important here that we need to talk about is um, um, uh, as temperature goes up, the mobility goes down and VT goes down. Okay, so then the question comes here on these devices, okay, and this is here because now we're talking about leakage and we're talking about the current. So as the temperature goes up, what happens to this device? Okay, why are we asking this question? Well, because when mobility reduces, this tend to reduce the current. When VT reduces, this tend to increase the current. So eventually, when we increase the temperature, what happens to the current? Does it go up or does it go down? Well, it turned out for the devices that are on, so this is VT, these are the devices that are on, and less than VT, these are the devices that are off. It turned out for the devices that are on, the reduction in mobility is dominant, and therefore you will see less current because of higher temperature. Not desirable. And for the off transistor, you will see more leakage current because of the VT is becoming dominant. Again, not desirable. So temperature makes me lose when the device for the when device is off and when device is on. When device is off, I will have more leakage current. Bad. When the device is on, higher temperature makes current less, and this is also bad. So that's why temperature is an enemy for semiconductor devices. We don't like higher temperature, let alone they tend to impact other factors, but one of the main things they tend to is to slow the device and increase leakage current, which is basically wasted energy. Okay. So here we come. Here we see that when we kind of as I indicated in the whiteboard, typically we say this is VT, and typically we say this is the behavior of the current versus VGS. Well, as I said, we lied there. The current doesn't go to zero. So this is the current here, IDS versus VGS, and you can see this is here the VT. All right, you can see that the current rolls off, and it's impacted with factors. One of them is DIBL because it does impact the leakage current in this region. Also, there is the gate induced drain leakage. Is there as well, and we'll talk about it later on. So this is the region of the subthreshold current. Okay, so as we indicated earlier, we reiterate that the subthreshold when for the device when it's on, when it is off, the gate leakage, it's when the device is on, and this junction leakage when because of the reverse biased diode current. Now, there are some models that estimates the subthreshold current, and they do have estimates for the gate. These are models a bit complex, and we don't intend to cover them in this class. We'll leave them for higher grade class and master degree or so. So we'll leave them for just reading material. Junction diode, we'll say, or junction leakage, sorry. There are two types here. There is the band-to-band there is the band-to-band. Let's see. Band-to-band and basically this is the current in these reverse bias diodes. And then there is the gate induced drain leakage, which is basically happens in this overlap region, between the drain and the gate. And basically there is a current occurs here, and it says that with the drain at high voltage and the gate as lower voltage, this is when we will see electrons moving, right, from the gate to the drain, and this is this current is proportional to the overlap area and the transistor width, because it increases the overlap area. And it's also a function of the electrical field, and rapidly with the drain to gate voltage, it's impacted with the gate to drain voltage. The band-to-band leakage is a function of the reverse bias and the doping levels. Okay, so band-to-band is because of these reverse bias, and gate-induced drain leakage is because of this overlap area, okay, between the drain and the gate. Okay, this is the reminder of the reverse bias diode that you covered in electronic class. And now finally here we go to some analysis question of DC analysis, and some of it's like some of the problems you will see in your assignments or your exam. So for example, here there is a circuit here, and you will see there is a PMOS here connected to a resistor, and this is a power supply. And the question says determine the required width of the transistor. So we need W here. Okay, so W over L is part of the current equation. We know L, which is he's given me 0.25 micron. He needs W such that this voltage Vx equals 1.5 volt. Okay, good. Now he says neglect short channel effects. Okay, which is channel length modulation. And this PMOS, he's given me the K prime factor, okay, and the VTO, the threshold. Okay, so the K prime factor, this is, we know that this beta, okay, and in some textbook they use K, so both are the same, okay? Okay, if we study this transistor, and choose a different color here, if we study this transistor, we'll see the current goes here to here, so this is from the source to the drain. Okay, so what is the drain voltage? 0 volt. How about the gate voltage? So this is the gate here. This is the gate. The gate is 0 volt as well. So VDS equals 0 minus Vx, which is minus Vx. VGS 0 minus Vx minus Vx. So this from VGS, which is minus 1.5, which is less than minus 0.4, which is the VT, that means the transistor is on. Okay, so we established that the transistor is on. Because so first of all, we have to decide if the transistor is it on or off. Okay, we established that the transistor is on. So we need to see what area it is. Okay, so the transistor, we have to compare VDS, which is minus Vx was minus 1.5 volt, okay, and VGS minus Vt, okay, which is minus 1.5 plus 0.4, which is minus 1.1. Well, this is larger than this. Okay, in the case of the PMOS, that means the device is in what region? Saturation. Okay, and in saturation, I know the current equation equals what? Well, the current equation equals this equation right here. Notice that multiplying the K prime by W over L, VGS minus VT square over 2. That's the current equation. But I know here there is a hint here. I have a power supply. I have a voltage here of 1.5. I can measure this. I can calculate this current. So this IDS equals 50 microampere. Okay, so 50 microampere. So I equate these two equations. The 50 microampere, I equate it with the equation of the saturation current. When I plug in all the parameters, I'll find that the only thing missing I need to calculate is W. Solve for W, and you get 0.688 micrometer for W. Okay, another example here, if I say with this circuit, okay, design a circuit so that ID equals a certain value. So this transistor, notice that the current goes like so. So this is the drain, this is the source. If you do VGS equals certain value, so this current is has a certain so this is the current here 1.8 micro, so this is equal 80 microampere. So we calculate the VD here, and it turned out that the VD equals 1 volt. Well, how did I calculate VD? Well, I have the current, I have the voltage here, I can calculate VD. If you compute VGS, it is so this is VG here is 1 volt. It is 1 volt, okay, which means it is on. So I established the transistor. Why it is on? Because the gate here has 1 volt, the source has 0 volt, so VGS, this is 1 volt, which is larger than VT. So he's telling me that VT is 0.6 volt. So the transistor is on. Now let's see in what region it is. If you see that with this kind of configuration, the VDS and VGS, the gate and the drain tied, this must be in saturation, okay? Because if you compute the relation, okay, so VDS and VGS minus VT. Well, this is 1 volt, all right, and this one is 1 volt minus 0.6 volt, and this is 0.4, and this is greater than. So VDS is larger than VGS minus VT, therefore it is in saturation. Now I apply the current equation for saturation, and I can see that I can solve for this equation. Okay, I can solve for this equation for ID, and basically I can solve for VD. Okay, now okay, now in case he did not give me R in the beginning, what do I have to do is I have to readjust my strategy, which is first solve for VDD, okay, and once I find out VDD, right, then I can find out R, because I know the value of the current, right, and I know so R becomes this equation VDD minus VD over ID. So so my earlier strategy depended on that I know R, but what if I don't know both R and VD? Well, first of all, I will solve for VD first, then use this equation to solve for R. Okay. With that, I conclude this section, and we will continue the lecture in the next part. Thank you.